Hi. Okay, we're going to look at problem. This is problem 8.7 in the book. This problem gets people hung up a little bit, and so we're going to go through and look at it. Now, for the record, this problem is the problem. It's the reason why I have not got rid of force triangles from what I teach from this book, because it really is easier, I think, to consider this with force triangles. I'm going to try to solve it without them, but still it helps to drive home some of the points. So let's do this. It says knowing that the coefficient of friction between the block and the incline is 0.25, determine A, the smallest value of P required to maintain the block in equilibrium and the corresponding value of beta. Okay, so basically what the question is how hard do we push and at what angle to keep this thing from sliding down? So let's do a free body diagram. I'm going to rewrite this a little bit. Okay, so at this point, so we got a bunch of forces acting on this point. Okay, we have a force P, and it's at this angle beta. We have a normal force coming off here. You can call that N. We have a force of friction coming off in this direction, and we have the weight of this thing coming down here. Okay, but what do we know about this force of friction? Since we're looking for that point just before it moves, this is N times mu sub S. Okay, so let's do our sum of my forces. So my sum of my forces in X equals 0. So what do you get? Well, the forces to the right are going to be this P force and this F force. So you have P, what is that, cosine beta plus F sine, I can call this is 60 degrees from right here. I can call it theta. Oh, I'll call it 60. Sine 60. Right, that's going to be, no, that's a lie. That's cosine 60 because we're talking F. So cosine, let's erase that and make it actually readable. And apparently erase the 60 as well. So that's going to be cosine of 60 is equal to, the only force in the other direction is the N. It's going to be N sine of 60, or it's cosine of 30, which is the same thing, right? This angle right here is 30. Okay. But again, we know what F is. That's not a complete unknown, so we're going to say P cosine of beta plus N mu sub S cosine of 60 is equal to N sine of 60. Okay, and now let's take the sum of forces in Y equals 0. And what do we have? In Y, we have P sine beta plus F, what is that, sine 60? Sine 60, and then plus, in this case, N cosine of 60 is equal to the weight, which is the weight, just to be, is 15 times 9.81. Okay, but I'm just going to refer to it as weight for the most part. Okay, but again, here we know what F is, so P sine beta plus N times mu sub S sine 60 plus N cos 60 is equal to weight. Okay, so right now we have 2 equations, but we have 1, 2, 3 unknowns. So that is obviously a problem. So this is where the force triangle concept comes into play. So let's draw this force triangle, but I'm going to do something in advance. I'm going to say, you know what, this normal force can be, this normal and the friction force that's supposed to go to the same point, I'm going to call that R, okay? So if we have some point here, we have the weight coming down, we have this R coming in this way, and then we need to close this thing to get to here, and this is my P, okay? And again, the nature, this is called R, okay, the nature of trying to minimize this is you always want to push perpendicular to the resultant force. So now we just have to figure out the angles of everything, and we can calculate that out. So now I'm going to zoom back in on this, hopefully. So hopefully this can be, you can see this. Oh, that's not looking good. Okay, so let's draw this again a little clearer, right? So you have this 60-degree line. You have this thing coming in here, normal to that. You have this force coming up here. And so we have this force there, So that is my R. So I know this angle, because if this is 60, therefore this is 30. So can I figure out this angle to calculate my total angle? Well, okay, we've done this before, but what do we know? Tangent of that angle, I'm going to call it phi, is opposite, which is friction over normal. But friction in this case, since it's at the limit just before it moves, is normal times mu sub s over normal. The normals cancel, therefore tangent of phi is mu sub s. So phi is tangent inverse of mu sub s. So it turns out that tangent inverse of 0.25 is, so therefore phi is 14.036. Okay, so that is this angle from here to there. So what is that angle in here? That's going to be from here to there, and we are looking for this angle is beta. So if that is 14 point, sorry, that is this angle here. So therefore, this angle, I'll call it alpha. Alpha is 30 plus phi, so it's equal to 44.036. And that is what we talked about here. This is alpha. So therefore, alpha plus beta plus 90 is equal to 180, or more to the point, beta is equal to 90 minus alpha. So therefore, beta is equal to, works out to be like 45.96 degrees. Okay, so now we know the angle that we're pushing on. And so now we'll come back to here, and we can come to this part right here. And all of a sudden, this beta, these beta terms are known. And so now we just have 1, 2 equations and 2 unknowns of p and n. And it turns out we don't even care about n. We're not being asked to calculate n. Please go up. Go down. Okay. So we're going to have to go through and just solve the 2 equations for the 2 unknowns. The way I did it is I took this equation, I solved this equation for n, and you get that n is equal to p cosine beta over sine 60 minus mu sub s cosine 60. I plug that n back into this equation, and okay, I end up with, so therefore, p sine beta plus, if I take this part right here and I factor out the n, I have n times mu sub s sine 60 plus cosine of 60 is equal to the weight. Plug this in for that, and I get with p, and I'm not going to bore you with all the details of that. You end up being that p, you have p sine beta plus p cosine of beta times mu sub s sine 60 plus cosine of 60, all that over sine 60 plus, or sorry, minus mu sub s cos 60 is equal to the w, and therefore p is equal to 105.786. And that is, and that's in newtons, that is the answer. So, again, to march forward, you just do free body diagram right here, all the forces, right? If they gave you beta, they said, hey, we're pushing at this angle, how far do you have to be, how hard do you have to push, then you'd be good to go. You could do it this way. Since they didn't give you beta, you have to come over to here and say, hey, what angle is beta? And beta is always going to be, sorry, well, not beta, but you're always going to push perpendicular to the resultant of the normal and the friction force, which is what we're calling this R vector. And that's how you minimize the amount of force that you have to push. And once you calculate beta, you come back to here, and it's just 2 equations and 2 unknowns. It's kind of 2 difficult equations, but it's just 2 equations and 2 unknowns, and you can solve for it. And that's that. Kind of as a gut check, the way I was thinking about this is, you're trying to think of this angle beta that we're trying to calculate. Well, if you were pushing, say, something around on ice, it's kind of natural to push pretty much just flat on the ice because the friction is very little, so you don't have to pick up a little bit, right? But if you're moving a couch around the family room, you definitely want to pick up a bit on the couch because it helps reduce the friction, and that's because the mu sub s of ice is much, 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 much lower than the mu sub s of carpet, and specifically of a couch on carpet. And so it makes sense that you're pushing perpendicular to that angle because basically the friction becomes zero, so that perpendicular to that angle on ice is almost just straight across the ice. So there you go. That is that problem, and we'll call that good.